Hello, welcome. This Henry, and on today's class, we're discussing freeze drying. Freeze drying. Under this topic, we'll be talking about the principle or the stages, the application, advantages, disadvantages, and the types. Now, freeze drying is defined or as what's good or what let me say freeze drying, also known as lyophilization or cryodesiccation, is a low temperature dehydration process that involves freezing the product, lowering pressure, then removing the ice by sublimation. It's like a method of dehydration that is commonly used in preservation of what, delicate substances. Now, before we dive into deep into this topic or this technique, we need to understand some basic terms, some concepts, and these are phase transition, phase diagram, triple point, sublimation, and lyophilization. Now, we need to understand one concept which is called state of matter. As you all know, that matter are things, or let me say things that occupy space, and have we have four types of them. We have the solid, the liquid, gaseous, and plasma. But the most important one of we'll be discussing here is the solid, the liquid, and what the gases. And before I move on, I would like you all to watch this video for a proper understanding. Proper on.
Do you know what water, air, and rocks all have in common? They are made of matter. Matter is something that takes up space. Now, you might be wondering why they all look so different if they are made of the same thing. But the truth is that everything around you is made of matter, just in different shapes and forms. Matter is made of tiny particles called atoms. Matter can be grouped into three main states: solid, liquid, or gas. To figure out which state of matter something is in, we need to examine its properties. A property is the way that something is that we can measure. The physical properties we will look at to determine state of matter are shape, mass, and volume. Mass is the amount of matter in an object. Volume is how much space that matter takes up. Solids are easy to recognize. Rocks, apples, pencils, and plants are all examples of solid objects. A solid object has a definite shape that doesn't change when you move it or put it in a container. They also have a consistent mass and volume. This is because the atoms in a solid object are packed closely together, so they do not move around. A solid will change shape only if forced, for instance, if it is broken or smashed. If you look around, you can find many examples of solid objects. Liquid is the next state of matter. Liquids have a definite volume and mass, but they do not have a definite shape. The atoms in liquid are still close together, but unlike the atoms in a solid, they can move around. This allows the matter in a liquid to flow. Because liquids don't have their own shape, they take their shape from their containers. The same amount of liquid may look very different in a glass and spilled on the floor. You can find examples of liquids around you too. Water, milk, and juice are just some of the liquids you might find. The third state of matter is gas. Gases have a definite mass, but they do not have a definite shape or volume. Like liquids, gases take the shape of their containers. Unlike liquids, gases will spread out to completely fill the container they are in. If a gas is not in a container, it will keep spreading out indefinitely. This is because the atoms in a gas are farther apart than atoms in a solid or a liquid, and so they can move freely. The air you breathe is an example of a gas. You might have noticed that you can't really see air. Often, gases are invisible, but they are still there. There are many different types of gases in the Earth's atmosphere, like oxygen, nitrogen, carbon dioxide, helium, and water vapor. Sometimes matter can change from one state to another. Water is a very good example of this. When water is frozen into ice, it is a solid. When it melts back into water, it is a liquid. When water evaporates into water vapor, it becomes a gas. Matter in all its states is everywhere. See if you can find solids, liquids, and gases around you.
Alright, welcome back. The next slide is phase transition. Phase transition. Now this term phase transition or phase change or phase conversion is most commonly used to describe transition or conversion between solid, liquid, and gaseous state of matter, as well as what plasma in rare cases. Now, during a phase transition of a given medium, certain properties like the volume, the density of that medium changes. So this could occur. I think this occurs because of some external conditions such as temperature and pressure. So the next video will explain more about this phase transition.
Our states of matter. Now we need to look at something that you'll see later on. This is what's called a phase change diagram or graph. And this shows us what happens with matter as we increase the amount of heat energy and what happens to the temperature, respectively. So we see here with solids, they have low amounts of heat energy. That means the atoms aren't moving around. So they would kind of condense like this, there wouldn't be a whole lot of space. As you add energy, you see these areas where it's flat. These are our actual phase changes. This is where we go from one state of matter to the next, either by melting a solid into a liquid, boiling a liquid to a gas, or going in the opposite way, condensing gases to liquids and freezing liquids to solids. The interesting thing about this, or the thing that you need to learn from, or that you need to get from this particular set of notes, is that during a phase change, so during this time period, temperature stays the same. What doesn't stay the same is heat energy. So heat energy is either added or released, depending on which way you're looking at. I'll move that up so you can see that. All right, so temperature is staying the same, which might seem a little counterintuitive. You know we have to heat up a solid in order for it to become a liquid, but what we don't see is that during that time where you have some solid, some liquid, that temperature is going to remain constant. The temperature itself will not increase until I fully change to the next state of matter. Okay? So, the other thing you need to be able to use or be able to interpret from this graph is a phase change endothermic or exothermic. If you remember from our chemistry or chemical reactions unit, something that is exothermic releases heat energy. The reaction loses that energy to the environment. And in an endothermic reaction, heat energy is absorbed from the environment. So we would have to look at this axis down here to tell if it's endothermic or exothermic. So let's take a look at melting and boiling. For both melting and boiling, I am adding heat energy to the system. I'm adding energy that makes these atoms move around faster. So these processes are endothermic. I have added heat energy to them. Let's look at condensing and freezing. So these things, so during these phase changes, and this might seem counterintuitive because we know when we freeze something it becomes cold, and we typically associate cold with endothermic. What's happening is heat energy is being released from these atoms to somewhere else. So these are actually exothermic because I'm reducing the amount of heat I have. I'm releasing that heat.
Yeah, welcome back. So the next slide explains a diagrammatic picture of phase changes. Please study this slide critically. Now, this next slide will talk about phase diagram. And there's a triple point here, critical point. Somewhere the next video will explain more about this graph chart. The next video will explain more.
We're going to talk about phase diagrams. Phase diagrams are a type of graph that relate pressure and temperature to the state of matter for a given substance. And so this is a phase diagram. On the y-axis, we graph the pressure, and so pressure is increasing as we move up. And on the x-axis, we include temperature, and so temperature increases as we move from left to right. And there's a couple of interesting things that we can see with a phase diagram. We could tell the state of matter for a substance at a given temperature and pressure. So for example, this represents water, this phase diagram. And so on this graph, right about here would be standard atmospheric pressure, which would be 1 atmosphere or 101.3 kilopascals. And then right about here would be 0 degrees Celsius, and so that's the freezing point of water. Now if we connect these lines, we can see that they meet right about here, and if we look at the boundary, this is the boundary between the states of solid and liquid. So this line right here represents melting and freezing. So at 1 atmosphere, standard atmospheric pressure and 0 degrees Celsius, we could say that is the melting point and the freezing point of water. Now if we extended this line right here at 1 atmosphere out like this, we're going to get to another point here, and if we bring this line downwards towards the bottom, I think we can make a prediction as to what the temperature would be. We're on the line where a liquid is going to be turning into a gas, so we're going to cross this barrier, which means we're going to have boiling, and so this would have to be 100 degrees Celsius for water, because that's the temperature that water boils at. Now there's some other interesting things here. So we have these boundaries where we can have solid turning to liquid, liquid turning to gas. We can even have solid going straight to gas. We call that sublimation. We also have a point right here where all the different lines converge, and we call that the triple point. At the triple point, we actually get solid, liquid, and gas all existing at the exact same point. The triple point is a really amazing phenomenon, and it happens at a very low pressure and low temperature for water. So we're way down below atmospheric and a little bit less than freezing for water. And we would literally see some liquid water that was frozen on top, so some ice, and we'd see it bubbling away as it boils as well. There's one other point that we can see here, and this is called the critical point. At this point right here, we no longer have a liquid and a gas existing at the same point. So if you can imagine boiling water, like in this kettle right here, we can see that we have both states of matter. There's liquid water, and you would probably see the steam rising, which is that vapor, as the liquid turns into a gas. Now, once we hit the critical point and we move out beyond this area, so if we're anywhere kind of in this region right here, we're going to have something called a supercritical fluid. And that supercritical substance is at the point where there's no longer a separation between liquid and gas. It just kind of becomes one thing. So it's kind of halfway between a liquid and a gas. So this is our phase diagram. That's some of the information we can gather from it. Some of the ways that we can change states include, number one, heating. Now this is probably the most common one. If you take some water and put it into a pan like this, put it on the burner, we're going to start raising the temperature. And so if we're sitting here with frozen water at this point and we just don't do anything to the pressure, we just start raising up that temperature, we'll eventually turn that substance into a liquid. Now we could also leave the temperature alone, so not adjust the temperature at all, and simply change the pressure. So here's an example of this. This is called a bell jar, this apparatus, where we have this plate here that have a bunch of holes in the top, and this jar, this glass jar that would fit over top, and we can create a vacuum inside that jar. So if we took a glass of water, put the bell jar on top, we have to attach here a vacuum. So we have this vacuum here that would start to suck out the air from this bell jar, lowering the pressure, so the pressure would decrease inside this jar. We could change this substance state without even touching the temperature. So maybe we're right here at standard pressure. It's hot enough to be a liquid, this water inside this glass, and we slowly lower the pressure. We could eventually turn that substance into a gas and we could start boiling it without even changing the temperature. We'll take a look at one last comparison here. We have two different phase diagrams, one for H2O, water, and one for CO2, carbon dioxide. Each substance is going to have a different looking phase diagram based on its unique properties. So for water, we can have water changing from a solid to a liquid at standard pressure. So remember, this is 1 atmosphere, and we had right here 0 degrees Celsius. And so at that point, we can see it's going to melt, right? It's change from a solid to a liquid. With CO2, if we had 1 atmosphere of pressure, that's standard pressure, and we started heating up that CO2 at standard pressure, it would pass directly from a solid to a gas. And this is why, if you've ever seen CO2, another name for it is dry ice, you can see it just starts kind of giving off smoke. So you may have seen something like this before. This is dry ice that's subliming. It's turning straight from a solid into a gas, and we get all that different vapor there. So every substance has a different looking phase diagram, and you can change the state of a substance by changing the temperature or changing the pressure. And so those are phase diagrams.
Welcome back. So the next slide is triple points. The triple points, as the former video explained, is that point that, or the temperature, let me say, is that temperature of a substance. Let me say, okay, the triple point of a substance is the temperature and pressure at which the three phases of that substance, gaseous, the liquid, and solid phase, it coexists in equilibrium. The next video will explain more about this concept. The next video will explain more about this concept.
Imagine the same substance existing as a solid, a liquid and a gas, all at the same time. Sounds impossible, doesn't it? It's what's known as the triple point, and we are going to demonstrate it now. Any pure substance can exist in 3 phases. It can be a solid, a liquid or a gas. We can show these phases using a pressure-temperature diagram called a PT diagram. This graph shows the location of the different phases of a pure substance in relation to pressure and temperature, with pressure P on the vertical axis and the temperature T on the horizontal axis. The 3 phases are separated from each other by so-called separation lines. There's a melting line between the solid and the liquid phase, a sublimation line between the solid and the gaseous phase, and the vaporization line between the liquid and the gaseous phase. The triple point is the location where all of these lines meet. It is specified by a certain pressure and temperature that is characteristic for each substance. If a pure substance is at these specified temperature and pressure values, all three phases will be present at the same time. One says that the three phases coexist. Pure water has a triple point temperature of 0.01 degrees Celsius and a triple point pressure of 611.5 Pascal. This is the same as about 0.6% of the usual atmospheric pressure. At this point, water will exist both as ice, as liquid, and as vapor. Let's see what this looks like in practice. For this experiment, we need a vacuum chamber which is connected to a vacuum pump. A combined pressure and temperature sensor is connected to the hose between chamber and pump. It is also connected to a PC via USB, and values of absolute pressure and temperature in degrees Celsius can be shown on the screen. Inside the chamber, we place a petri dish with liquid water. After the chamber has been sealed, the pump is switched on. Both pressure and temperature start decreasing immediately. During evacuation, the liquid water starts to boil as the pressure drops to the saturation pressure at the given temperature. The glass beads reduce the splashing of water during boiling while the pressure decreases. They will also provide nucleation sites for the other two phases. While the pressure drops quite quickly, it takes longer for the temperature to approach values around 0.01 degrees Celsius. Unfortunately, our pressure sensor cannot measure below 1.2 kilopascal, but we will see later that the pressure is low enough as the water will be in all three phases. This can, however, take a few minutes. After some time, we see both formation of ice on the surface of the liquid water and that vapor bubbles appear in the liquid. We now have a situation where the water is boiling under a thick layer of ice. This is water at its triple point. All three phases coexist. The different phases are, however, not in equilibrium, as the amount of water in each of the phases changes with time. When we switch off the pump, the water will be stable at the triple point as long as the chamber manages to hold the necessary pressure and temperature conditions. Once we open the inlet valve and increase the pressure back to normal, we can see that the vapor bubbles disappear first. Small droplets on the glass bell eventually evaporate and the ice in the petri dish begins to melt. In a second run of the experiment, we also place...
Well, welcome back. I hope you all do understand that concept. The next slide, we'll talk about sublimation. Sublimation, according to this definition, is the transition or the conversion of a substance directly from both the solid phase to the gaseous state without going through the liquid state. So this diagram here represents the definition of sublimation. The next video will explain better how this concept.
Hey, what's up? It's Mr. J with Cy and the Fly. Today, we're talking about dry ice. So what is dry ice? Dry ice is simply carbon dioxide that's been frozen. We find carbon dioxide everywhere. We find it in the atmosphere. We find it when we exhale, when we breathe. We find it in our soft drinks. That's what adds the carbonation. Carbon dioxide's everywhere. We can do a lot of really fun stuff with it when it's frozen. And I say frozen, I mean really frozen. This is negative 110 degrees Fahrenheit or negative 78.5 degrees Celsius. This is very cold, which is why I'm wearing my glove today. It's very dangerous if you touch it to your skin. So if you're doing this at home, you can definitely want to make sure you're wearing a glove. Some people ask me where you can find dry ice, and actually it's more common than what you might think. You can find it at a lot of supermarkets. I know there's a local supermarket here in town that carries dry ice, but I find the best price at a local welding supplies vendor. So just kind of look around, call around, and I guarantee you can find it in your hometown. One of the really fun things to do with dry ice, and a lot of people do it during Halloween time, is they simply throw it in some water and kind of make it that foggy, mist, scary look. What I have here is a very large beaker, 3,500 milliliter beaker, and I've warmed up the water, and what I'm going to do is I'm going to place this dry ice into the water. And what I would like for you to do is just observe what's happening. Right now you can see a little bit of this fog coming off of the dry ice because of the room temperature versus the negative 110 degrees below zero temperature of this ice. When I do this, I'm going to place it in there, and immediately what you're going to see is you're going to see a very quick reaction. What's happening here is called sublimation. We have solids, liquids, and gases are our three main states of matter. The solid, which has molecules that are tightly pressed in together, vibrating, which was what the molecules look like in that dry ice. When I place them into the liquid, the molecules in the liquid are slightly sliding past one another. And then immediately you get gas, which is this right here, which is perfectly fine to touch, and it actually feels rather warm. Gas molecules are spread apart, and they're moving quickly. Sublimation is the process of which solids turn directly into a gas. They completely miss the liquid wet state, which is why we call it a dry ice. So I showed you how we can do some really cool fog effects for Halloween. What I'd like to show you today is some dry ice bubbles. Now this is really cool, especially if you have something that has a smooth, level rim. The beaker here that we were using earlier had this little lip here. Sometimes that really doesn't help us make the bubble that we would like. So I'm going to use this giant flask, and we have a level edge. This is great too if you do this experiment with kids or whatever. They can't really stick their hands inside of it, so it's safe. Like I said earlier, make sure that you're wearing gloves. I have some dry ice here that I would like to put in the flask, but beforehand, I kind of want to make it a little extra cool. So I'm going to add just a couple of drops of food coloring here, just a little bit to give us a little cool factor. I'm going to let that dilute there. And as that's going, I'm going to place this dry ice into the flask just like I did with the beaker, and you'll see sublimation occurring. The ice is subliming in the warm water. Remember, the warmer the better. And as I place the ice into the flask, immediately you see a really cool effect, just like you did with the beaker. Now what we're going to do here is, ahead of time I've mixed some soap and some water into a small bowl and soaked a string, a shoe.
Yeah, welcome back. I hope you do understand in that video. The next slide is now in continuation from the other slide, the previous slide. Sublimation is an endothermic process, which means it requires what? Heat. So to occur, and this endothermic process occurs at temperatures and pressures below a substance triple point from the former video, and it's in its phase diagram, which corresponds to the lowest pressure at which the substance can exist as a liquid. And this, the other videos have explained this this information here. And note, in freeze drying, now coming towards our technique. In freeze drying, the material to be dehydrated is frozen at low temperature, and its water is what allowed to sublime under reduced pressure or vacuum from that other video. Now, lyophilization, let me redirect you to a video that better explains this concept. Lyophilization is also known as what? Freeze drying. So let me go to the next video for a better explanation.
We lyophilize products when they're not stable in a liquid formulation. A product that is stable for maybe weeks in liquid might be stable for years, 2 to 3 years, in a lyophilized state. And that is the prerequisite to get it to the market and get it to the patient. 12 months stability is usually the minimum that will be accepted by the authorities. For the lyophilization, the product is filled into the containers, into the syringes or the vials, and is then frozen in the lyophilizer. The freezing immobilizes all the constituents, all the things that we have in the solution to be freeze-dried. And after a certain time, at say -50 degrees Celsius, we start the drying process by applying a vacuum, which will then drive the sublimation. Sublimation is when the water goes directly from the ice state into the gas state, bypassing the liquid phase. And this is what makes lyophilization a very gentle process. At the same time, it's a time-consuming process, and it might take between 20 and 120 hours to complete.
Yeah, now to the real deal. Freeze drying, like all said, is known as lyophilization method. It's also known as cryodesiccation. Now, this next video will explain technically everything about freeze drying. So hold on.
Hello. So in this video we are going to learn about freeze dryer. So these are the contents that we are going to cover up in this video. So this is the introduction. As you can see, the freeze dryer does freezing and has important applications in the pharmaceutical and biotechnology industries. Freeze drying is now a standard process used to stabilize, store or increase the shelf life of drug and other biological products. So here comes the principle of freeze drying. So it is based upon the process lyophilization. So what is lyophilization? So lyophilization, or also known as cryodesiccation, is a process of dehydration which involves the dehydration in low temperature and low pressure, and this causes the removal of ice by sublimation. So what happens, as first comes in our mind, that in drying, what happens, the moisture in our material is dried and it is converted to ice by the low temperature, and then applying low pressure, that ice gets sublimized to its gaseous form, that is the vapor state. So here comes the diagrammatic representation of our freeze dryer. So first of all, there is a door. When we will open the door, we will see some plates stacked upon one another on which we can place our samples. These plates are perforated. Why perforated? I will tell just right now. So at the base of this drying chamber there is a heating system. So this heating system releases hot air, and there is a fan rotating here. So this fan causes what? It circulates the whole hot air in a uniform manner inside this chamber. As I have told you, there are perforations present on these plates. So there are perforations on these plates, but why do we need that? So what you are seeing right now is the side view of this whole chamber. So from the top, the plate looks like this, and these are the perforations on the plates. So why do we need these perforations? So at the bottom of this chamber there is a heating system, and from this heating system hot air comes up for drying. So this hot air needs to be circulated throughout this heating chamber properly. So it has to reach even the top plate very well. So we need this perforation so that this hot air can pass through these perforations and reach up to the top plate and dry the whole chamber in a uniform manner, so that the drying process become efficient. But that not happens at the beginning. So from at the beginning, what happens that there is a refrigerator unit which works first. So there is a sample placed above the plate, and the refrigerator unit does what? It decreases the temperature at about -20 degrees centigrade, which is very low temperature. So at this temperature, the moisture content present in our sample becomes ice. So it freezes and converts into ice. Now there is a vacuum pump. So this vacuum pump does what? It decreases the pressure and then heating system is turned on. So what happened that first of all we decrease the temperature using this refrigerator unit up to minus 20 degrees centigrade. So at that point all the moisture content inside our sample converted to ice. Then we turned on the vacuum pump, which causes what? It decreased the pressure inside this drying chamber. Then heat is applied. So when at a low pressure heat is applied, when temperature is increased, then it causes sublimation. So the ice at the surface of a sample got sublimized to vapor. So it converted from the solid ice to a vapor state. So this sublimation occurred due to the low pressure and a little bit high temperature. So now this vapor is collected in this ice condenser, where it is again converted back into ice from the vapor state. Now the solid ice is removed using this drainage system. So what happened from the beginning, that there is a refrigerator unit which decreased the temperature at a very low temperature, where all the moisture content in our sample got freezed and converted to ice. Then the vacuum pump is turned on, which decreased the pressure, and then the heating system is turned on. So now it is called the primary heating. So this primary heating does what? It increases the temperature gradually, and with increase in temperature at a low pressure, sublimation occurs, which converts the ice present on our sample to vapor. And this vapor is collected by this ice condenser, and it converted it into solid ice, and it is drained out through this outlet. Here comes the procedure of freeze drying. So the first stage is the pre-freezing. So at this stage the material is frozen at very low temperature, that is minus 20 degrees Celsius to minus 30 degrees Celsius. So the second stage is the vacuum. So at this stage the vacuum pump is used to reduce the pressure inside the chamber. Now comes the primary drying. So we already achieved low pressure by applying the vacuum. Now in primary drying we have to increase the temperature inside the chamber. So what will happen due to this? So due to this, sublimation will occur. So you can see there is a graph here. So this graph is pressure versus temperature graph, and this point is called the triplet point. So if we take the triplet point as our reference, so if we draw a line against the pressure, so below this pressure, if we apply temperature, the solid will convert to the vapor phase. So by this pressure temperature graph, it can be cleared that below a certain pressure, if we apply temperature, our substance will sublimize from the solid state, here it is ice, to the vapor state. And now this vapor reaches the condenser, that is the ice condenser, which is a separate unit from the chamber, from the drying chamber. So it is a separate unit where the vapor reaches and again condenses back to its frozen ice. So the vapor is again converted to solid ice at a separate chamber, which is known as the condenser. And this frozen ice, that is solid, is very much easy to be removed by the outlet. So this is how we can achieve drying, that is the removal of water from our substance, maybe it can be drug or any biological product. So this is our last step, that is the secondary drying. So here we increase the temperature gradually up to 50 degrees Celsius, not more than that. As we are dealing with heat sensitive products, so it might get degraded. So what we can do, we can increase the temperature up to a certain value where the product doesn't get destroyed. So we are doing this to extract almost all remaining bound moisture from the product. See, 100% drying is not possible. we cannot remove 100% of moisture from any product. That is the universal truth. But we can try to achieve as much as possible we can. So gradually increasing temperature up to 50 degrees Celsius, not more than that. So this is the threshold value. If we increase temperature above 50 degrees Celsius, then it can damage our product because they are heat sensitive. So here comes the purpose and use of freeze drying. So in your mind, question can arise that why we are using this freeze drying. Instead we can apply heat and extract all the moisture from our product. Maybe it is a drug or any biological product. So we can apply heat. So why not we are using heat to extract all the moisture from our substance? So what happens that there are certain substances, some drugs, some biological products which are very much heat sensitive. That means at higher temperature, these substances, these drugs, these biological products will degrade and we will lose their quality. So what we can do, we can freeze dry those things and still attain the same goal. So products like vaccine, antibiotics, penicillin, blood plasma, protein, enzymes, hormones, all these things are freeze dried because they are heat sensitive. So these are the advantages of freeze drying technique. So the main advantage of freeze drying technique is that now we can dry up the drugs which are heat sensitive. And here are the disadvantages. So the main disadvantage of this process is that it is very much costly. So the whole process of freeze drying is very much expensive and difficult to maintain. So this was the brief explanation.
Welcome back. I hope this did justice to the work. Thank you very much. So I would love to hear from you. Questions.